This video is on lesson 8.3 and we're going to be going over asymptotes. So I'm going to assume that you guys know about asymptotes. These are lines that your function never touches but gets really close to. I mean, sometimes it touches it, but for the most part, it just usually brushes really close to it. And so we learned about that in advanced functions. And we allowed you guys to use tables to analyze the end behaviors of your function as they approach these asymptotic lines. Now, since we're in calculus, we're going to take like a calculus spin on it, which means no more tables, only limits. Okay, so this video is kind of like a review, but then also has a little bit of a calculus spin. So let's get into vertical asymptotes first, because the other ones are a little bit more tricky. Vertical asymptotes are pretty easy. You just look at the denominator and you say, that can't equal to 0 because if it does, we have a problem. Let's take a look at when it equals to 0. So factoring the bottom, I'm going to get something like this. And that's going to equal to 0, so if I solve it, I'm going to get -5 and 3. So if x is -5 or 3, the denominator will make a 0. Which is not what I want. That's going to give me problems. So I don't want it to equal to 0, which means I don't want these x's to equal to -5 or 3. That's where I'm going to have my vertical asymptotes then. So here's where it gets a little bit tricky. The way that we write a vertical asymptote, because a vertical line has an equation of x equals to. So we're going to put -5 because that's where I want my dotted line on my graph where my function will not touch. So I know it's kind of confusing that I wrote does not equal to -5. It's because the value of x cannot equal to -5. However, the line itself has an equation of x equals to -5. So then I would have another one that says x equals to 3. So both of these would be my vertical asymptotes. Let's check out a couple questions. Okay, so example number 1. Determine any vertical asymptotes and its behavior for a certain function. I put the function in blue and then factored out the bottom. It makes it a little bit easier to see what x can't be. Once I have those two numbers, those are going to dictate my equations of the lines. So again, that's why we have equal signs of where my function can't touch. So the vertical asymptotes are 3 and -2. Now, before I get into the behavior, I'm going to keep going up and down, sliding, sorry, just to show you the graph. So here we have both of the asymptotes already at -2 and 3, and they're vertical. Now I want to see, well, where is my graph? Like, where is the function? How does it look and behave as it gets closer to these lines? So let's look at the leftmost one first. Instead of making a table, I'm going to start doing limits. So as x approaches -2 from the left, I don't know, like -2.01, I can sub that number into my original function, so this is a blue function, wherever I have an x. So we're going to put that in our x's, and we get a huge negative number. Whereas if I choose something to the right of -2, like say -1.99, sub it into wherever I have an x, I get a huge positive number. That means that my blue function coming in towards the first vertical line on the left-hand side, coming towards -2 from the left, I'm going to have negative end behavior towards -infinity. Whereas if I'm coming from the right-hand side towards -1.99, I'm going to get a really large positive number. So those are the ends of my graph. And then I'm going to do the exact same thing for the 3. So 3 from the left and 3 from the right, I'm going to get these two behaviors. And so the one on the left, as I'm approaching 3 from the left, I get a -infinity. Whereas approaching from the right, I get +infinity. Now, what I would do next is I would actually do further analysis if I really wanted to get like an accurate graph. I would start to look at concavity. I would start looking at like local extrema, maybe some x and y intercepts in there, points of inflection, and just put it all together in order to get like a really clean, beautiful graph, which is essentially what I'm going to be doing in the next 2 videos. Okay, let's keep going. So here's another one. We have our original function. I'm going to factor out the denominator to make sure that I can see my vertical asymptotes. Now this one has a little bit of a catch. Notice that the top and bottom can cancel out. If that ever happens, it means you have a hole. That's not a vertical asymptote. It means you have a hole, a removable discontinuity in your graph. Okay, and so if you really want to know where it is, you can always take x equals to -1, because this is x equals to -1, and sub it into your finalized function. So we can analyze where that hole is by subbing it into f at x, and I see that the hole is actually at -1.5. I'm going to scroll down to my graph and just put that in for now. So -1 looks like it's around here, and maybe we'll just say that that's a half. Our graph doesn't exist here because there's going to be a hole. Okay, now let's check out our vertical asymptote. Well, do you see how our denominator is this? It's going to give rise to an x value of -3 that gives us a problem. And so the vertical asymptote is going to be at -3. And when I analyze from the left and the right, I get -infinity and +infinity. So coming in from the left-hand side, we're going to get closer and closer to giant negative numbers. And coming in from the right of -3, I'm going to get giant positive numbers. Okay, and again, if I wanted to draw the rest of my graph, I'd probably have to do some further analysis because, I mean, what does it look like? It has to connect with that hole at some point, I assume, but I don't know. Let's focus on another type of asymptote that we kind of heard about before, a horizontal asymptote. So horizontal asymptotes look kind of like this. They start with y equals 2 and then have some sort of number, because y equals 2 and then some number is a flat line with no slope, right? Our graph is going to approach this line but never touch it. And so if it approaches from the top, it might look like this. This is if it approaches -infinity. So as your x values get smaller and smaller, your graph is going to get closer and closer to that pink line. It could also come from the bottom as well. On the other side, we're going to approach +infinity. So as your x values get larger and larger, your graph can either approach the pink line from the top or the bottom. Now, we check that by doing limits of the function at a very low and a very high number. So we sub huge positive and negative numbers into our formula, and then we see what our answer is. And we compare that to whatever this number is. Now, this right here just says that your function could technically cross over the horizontal asymptote. I've seen that before, but we're not really interested in where they actually cross. We're just kind of interested in how they're approaching your pink line. So the other one, the last type of asymptote, is your oblique asymptotes. Okay, now this kind of looks kind of crazy, but let me give you a very simple example. So oblique asymptotes a lot of times are when you have a higher degree polynomial, so something like this, being divided by a smaller degree polynomial. And so let me give you a very easy example. Forget polynomials, let's just talk about numbers. Okay, so you can do 7 divided by 2, right? Goes in 3 times, you're going to get a 6. Subtract and you get a 1. This guy in here, which was our polynomial before, I'm going to put a P for polynomial. That's this. It's being divided by something called a divisor. That's this. Your answer is going to be a quotient. That's this guy. This guy down here is your remainder. And then the way that we write this all in a mathematical sentence, so some sort of equation, is it would make sense if the divisor was under there. So let me show you this equation, this sentence, with respect to all of these regular numbers. So the polynomial over your divisor is equal to your quotient plus the remainder over your divisor. So this makes sense, right? This should be 3.5, and this is 3.5. When we do something like this, your oblique asymptote is actually always your quotient. And so the reason for that is because when you take the limit from the positive and negative infinity towards your function, what's going to happen is this guy right here ends up usually becoming 0. So it becomes negligible, and therefore your answer is actually just this guy. So that is your oblique asymptote when you approach from positive and negative infinity towards your function. So I'm going to give you some examples of this. I know it's a little bit rushed because I have a lot of examples. Essentially, you're going to find your horizontal asymptotes only when your numerator's degree is less than your denominators. If they're equal, you'll also have a horizontal asymptote. But if you ever have it so that the numerator is a larger polynomial degree than your denominator, you can then do the polynomial division, which means you'll get an oblique asymptote. For the first one, you usually get a y equals 0 for your horizontal asymptote, and this one you'll usually get a fraction. So I'll show you what happens through some examples. But one other thing that I really want to note before you actually get into some examples is if you ever have an x at the bottom of a fraction and you try to sub in positive, negative, infinity, you'll actually get 1 divided by a huge number, positive or negative, and that actually equals to 0. Excuse me. So, same thing over here and same thing over here. Basically, if you have an x in the bottom and you try to sub in a huge number, positive or negative, it's going to become a negligible number. So there's no point in looking at it. We're going to see stuff like that when we start to analyze the horizontal asymptotes. Okay, so this question is just saying, give me the vertical and horizontal asymptotes, and obliques if you can find them. So the first thing I'm going to do is I'm going to look at the denominator and see if there's a vertical asymptote. Is there a value that x can't be because it'll make the denominator a 0? And in this case, there is none. Because even if I bring the 1 to the other side, I can't square root a negative number. So we have no vertical asymptotes. For the horizontal asymptote, I have a horizontal asymptote because the top has a degree 1 and the bottom has a degree 2. Since the top is smaller than the bottom, we get a horizontal asymptote. And we can find that horizontal asymptote by taking the largest degree polynomial, so this guy right here, x squared, and we're going to divide every single term by x squared. So this guy's going to be divided by x squared, this guy's going to be divided by x squared, and this guy's going to be divided by x squared. So everything that originally existed in the function itself. And we're going to take the limit as x approaches positive, negative, infinity. Because we want to test, again, as x approaches bigger and bigger numbers, what is the end behavior that's getting closer to that horizontal line? And as we get to smaller and smaller numbers, what is the end behavior of my function getting closer and closer to that horizontal line? So like I said, this, when you break it down, equals to 1. But when we have an x at the bottom and we sub infinity into it, this is going to become a 0. So this guy right here becomes a 0. We can break this down a little bit and you get 1 over x. But again, this x, once I sub in infinity, is going to give me a 0. And so the overall fraction is going to be 0, which means I get a horizontal asymptote of y equals to 0. That's basically what we said in the rule in the previous slide, that if you ever have a numerator with a degree that's smaller than the denominator's degree, you're probably going to get a horizontal asymptote of y equals to 0. Okay, so B. This guy right here, looking for a vertical asymptote. Okay, so this one, I actually needed to do a difference of cubes. So I recognize that this is something cubed and this is something cubed. See? So I took the cubed root of each one and I got my x and y. I can also put it into here. So by the way, this is what happens when you factor out like a difference of cubes. From this bracket, I got an x value of 0.79 as a vertical asymptote. But this one did not have vertical asymptotes, like I couldn't solve it. And so I got some imaginary numbers. If I were to graph this, obviously you can't graph imaginary numbers. So this would be the only vertical asymptote that we would actually graph. Okay, now horizontal asymptote, actually I can't slide down yet. The top and bottom have the same degree. And so we said that when we have the same degree, those polynomials, or those terms I should say, the coefficients of those terms, will be your horizontal asymptote. We can use limits to actually figure that out. So I'm going to take the largest degree, which is the x cubed, and I'm going to divide all of my terms by x cubed. I'm going to reduce it, and so on the top you're going to get a 1, right? These guys are going to become a 1, and so I can't really do anything with this one, so I'm just going to rewrite it. But when I sub in the positive negative 1,000, this guy becomes negligible. It becomes a 0. And so as you can see, I get my horizontal asymptote of y equals 1/2. All right, so this one has an oblique asymptote because, and I'm sure you guys can look at the vertical asymptote first, this degree is higher than this degree. So that means we can do some polynomial division, which I'm not going to go through. But you see your quotient. This guy is your polynomial. This is your divisor. You got your remainder. And so writing it into your formula for f at x, this guy is going to be your oblique asymptote. And we can prove that with limits. And so we test that with a positive, negative, infinity. And we say, okay, if we take the limits of your q and your r over d, this guy is going to become a 0 if you sub in positive or negative infinity into that denominator. So we don't really care about that too much, whereas the other one is just going to try and approach this line. And so we get a final oblique asymptote of just that line. It'll look something like this. And so on the right-hand side, you'll see my y equals 2x minus 2 linear line. Okay, and the way that we test is we're going to use some x values, some large and small x values. So this one is very close to negative, well, it's not really close to negative infinity, but it's a huge negative number. We're going to sub it into f at x and see where it is. So if I took like negative 100, I'm going to sub it in to f at x and I get negative 202.03. If I compare it to if I subbed in negative 100 into my oblique asymptote, I mean like, let me get my, if I extended this guy, right, this is eventually going to touch right there. And I'm going to extend this guy just to make my point. This would be negative 202, which is this. So your function is actually going to lie below that at negative 202.03. So it's close, which means it's going to be approaching like this from below, okay, which is what this statement says. If you pick something like 100, so something all the way over here, 100, your oblique asymptote, which I'm going to have to stretch again, okay, so maybe somewhere up here is going to be 198. But if you sub in your function, 100 into your function, it's going to be a little tiny bit above that at 198.03. So you're going to be approaching from above. That's how you test your end behaviors for your oblique asymptote. Okay, so I got a couple more examples that I'm going to run through really quickly, but I'm just going to show you again that when you have your limits for your horizontal asymptote, they should look like y equals 2 and some sort of number. So that's what b represents. And this is only true if approaching positive infinity, your graph is going to approach super, super close to your horizontal asymptote, either from above or below. And if you're going towards negative infinity, again, your graph should approach from above or below. So we'll see a couple of these examples in 2 seconds. Okay, example number 4. Determine all asymptotes and their behaviors. So the vertical asymptote is going to be found right down here. It can't be 5. And so that gives rise to our first asymptote. And we can test it from the left and the right by choosing numbers that are a little bit left and a little bit right of 5. And so we get these two. Let's put those two in before we forget anything. Okay, so here's my graph. All right, and you'll see in the light, cyan color or whatever, it's going to be going this way and going this way. All right, now let's take a look at our horizontal. And by the way, I knew that I had a horizontal because if you look at the degrees, the degree on the top is a degree of 0, whereas a degree on the bottom is a degree of 1. And so the top is less than the bottom, which gives rise to a horizontal asymptote. We can take our function and do the limit as x approaches infinity. Okay, so again, dividing by the highest degree. And as we break it down, you'll notice that y is equal to 0. So that's going to be our horizontal asymptote. And we can always test with x values, something that's super close to negative infinity and positive infinity for both our function compared to our horizontal asymptote. So that 0 came from the fact that our y equals to 0. So this one looks like it's below the horizontal asymptote, whereas this one looks like it's above the horizontal asymptote. So we'll get our function, here's the above, here's the below, and so our function will probably do one of these, and this will be our f at x. Okay, so example number 5, and then I have a little tiny bit of a smaller question. Determine all asymptotes and their behaviors for the following function. So again, vertical asymptotes, look at the bottom, see if you can factor that. In this case, I saw it's called I think it's not called a difference of cubes. Sorry, I didn't write that right. I think that is factorable. I just don't remember it myself. And so looking at my colleague's notes, she was able to factor, I don't know what it's called, like a sum of cubes, I guess. I think that's something like x cubed plus y cubed is x plus y, x squared minus xy plus y squared. I believe that that's the formula for a sum of cubes, and that's where this came from. So factoring that, you should be able to solve for your vertical asymptotes. This one, again, is negligible because it's something that requires imaginary numbers, and so you don't have to really consider that when you draw your analysis. So checking from the left and the right of -1, we get towards positive and negative infinity. Okay, so why don't we draw that first? Okay, coming in from the left, positive infinity. Coming in from the right, negative infinity. Now going back to the original question, I want to see why I had horizontal asymptotes. Okay, so checking out the degrees on the top and bottom, they're both the same. And so that means that we have a horizontal asymptote. and we can do an analysis with positive and negative infinity limits. So dividing every single term by the largest degree eventually simplifies to a horizontal asymptote of just positive 3. Okay, so when we do our analysis of numbers that approach negative infinity and positive infinity, you'll start to notice that f at x is above 3, which is our horizontal asymptote. So I'm going to draw that in first. As it approaches negative infinity, it's going to be above our 3. Approaching 100, we're going to be below that 3. So approaching 100, it is below this 3. So we can kind of figure out what the rest looks like. I mean, you just connect these guys, and these guys would just connect together too, and that would be our f at x. So you're probably going to ask, like, those are kind of sketchy, like the sketches itself. Again, if you want to be more accurate, you would just add in like x and y intercepts and do further analysis. So the last question is example number 6, find the equation of the linear oblique asymptote of each curve. You can tell that there's an oblique asymptote because the top degree is larger than the bottom degree. So you're just going to do polynomial division. And again, I'm not going to go through all of this. Just know that this guy right here, which we find at the end, is going to be our oblique asymptote. Same with this one. After we do our division, ends up the same down here, and again is our oblique asymptote. So that was our super long review of asymptotes. And the next 2 videos will be our last for this unit, and we're going to go over and make everything one complete vision. See you later. Have a great day.